Hi everyone, my name is Thomas Kim. Today is June 30th, 2022. This is my 18th episode about C++ 17 2023 CUDA, SYCL, OpenGL, OpenCL, TBB. This is also third episode about TBB internals. By third episode, I mean there are two more videos about TBB internals. In episode 16, TBB internals 2. In episode 15, TBB internals 1. By internals, we are going down deep into the core implementation of Intel TBB library, or is called TBB task. Please download Intel TBB learning materials by clicking this link. It is 176 megabytes. It includes 2 PDF books about Intel TBB or threading building blocks. Also, Intel TBB official sample code. When download is complete, click this button, Show in folder, unzip it on your machine. In this folder, you can find Intel TBB, this PDF book. Also, ProTBB, this PDF book. Also, 3 pretty icons. Now, I changed the icon for my command prompt like this for Intel TBB version 2020. This folder also includes Intel TBB version 2020.1 for Windows, Intel TBB 2019 for Windows, also ProTBB master. In this folder, ProTBB master, you can find all sample code for this book. Also, you can find 1 TBB master. 1 TBB master examples. These examples are for 1 TBB version 12. Most of the source code in 1 TBB master in this folder does not work with older version Intel TBB 2020. The reason I installed older version TBB 2020 is that I want to learn how TBB task works behind the scene. In this book, chapter 10, using task to create your own algorithm. If you scroll down in the page 284, you can find the low-level task interface, part 1 blocking. In this episode, I discuss part 1 task blocking. Now, scroll down. Low-level task interface, part 2 task continuation. I will discuss task continuation in my next episode. Also, scroll down. Low-level task interface, part 3 task recycling. I will create at least 3 or up to 6 or 7 videos about TBB task, the low-level task interface. So, if you understand chapter 10 completely, you can understand this whole book. Chapter 10 is the most challenging and the most difficult chapter in this book. Without further ado, let's get started. Open up your Visual Studio Code. Select CPP 17 2023 Parallel. Select empty place, click New Folder 018 Task Blocking. Click this button, Blocking .cpp, hit Enter. Ctrl B. I will close Get Started. Ctrl Shift P. Edit Configuration JSON. I will disable Include Macro. I will enable TBB Order Inc. If you do not have this environment variable, you haven't installed this Intel TBB 2020, the older version. In such case, you have to watch my previous video. I will arrange side by side. Select low-level Task Interface Part 1 Task Blocking. I will make it bigger, fit width, scroll down. We will implement this part. I will arrange side by side like this. Here, include talkplay fun output HPP, talkplay fun S-stream print, auto L value reference NL, talkplay fun NL, auto L value reference NL, talkplay fun NL. For it, we will create Fibonacci sequence like this. Long fib, long n. If n less than 2 or n equals 0 or 1, we simply return n. Else, return fib, n minus 1 plus fib, n minus 2. This is recursive function call. Don't concern about the performance of this algorithm. We are not interested in performance of Fibonacci sequence. We simply use it to understand how Intel TBB task interface works. Now, scroll down. Here, class pib task, public TBB task. Don't miss semicolon here. Public const long n, long pointer const sum, const long point sum is different. Long pointer const sum. If you do not understand why these two are different, you are probably not ready to understand or watch this video. We will create constructor long n underscore long pointer sum underscore n underscore sum underscore. This is constructor. This TBB task is virtual class. This base class declares a virtual member function. TBB task pointer execute. We can say override. This is virtual function declared in the TBB task base class, so we have to provide implementation. If n less than cut off we simply call pib n, then assign it to sum. This sum is pointer, so we need to dereference. This cutoff I will define it here. Template long cut off. Here, else we create long x, y function local variables pivot task L value reference A. It should be L value reference because we will dereference. New, we are using placement new operator. TBB task allocate child. Please take note this part of code. We are allocating pivot task n-1. We pass x semicolon. I will give a line break here. This is called placement new operator. It returns pointer. This is not pointer. This is L value reference. So we dereference. Please note that this constructor pivot task takes two values, n and sum. This is n-1. This is for new sum. This is recursive definition. This x corresponds to this template parameter sum. So this sum points to local variable x. I will copy this, paste b n-2 y. So we defined a, b. Now this part. Please understand that we can do this, or we can say this allocate child. This is the same. So we are creating a new child pivot task A, a new child B, pivot task B. Now here this set reference count 3. This current pivot task has 1, 2, 2 children, but we set 3, k number of children. We have to provide k plus 1 as argument to set reference count. So 3. The reason is that this is blocking task. This spawn, we spawn B. It means push B into TBB threads task stack. I said stack. Stack is last in, first out, or LIFO. Now this spawn and wait for all A. We push it A on the top of TBB threads task stack. Once again, stack is last in, first out. So this A will be executed prior to task B. But there are some other implications too. Anything wait is blocking operation. By blocking operation, task A, task B will be executed by TBB task scheduler. When execution of A and execution of B are complete, then control returns. When task A runs to completion, it decrements its successor or its parent's reference count by 1. So after executing A's parent, this object, its reference count is decremented by 1. So it becomes 2. After executing child B, it also decrements its parent's reference count by 1. So at this point, reference count becomes 1. If this reference count becomes 0, TBB task scheduler deletes this object. So if this object's reference count becomes 0, current task, this task is removed or deleted by the TBB task scheduler. But in this case, when A is destroyed, reference count becomes 2. When B is destroyed, reference count becomes 1. So after this operation, reference count is still 1. So this part is executed. Sum x plus y. When task A is completed, the value of x, this value is determined. When child B completes its operation, the value of y, this value of y is determined. So at this point, x and y are determined, and its sum becomes the value of sum. Now we return null PTR because we are in execute function. We can return null pointer. I will fold it up. So sorry, this null PTR should come here. So I will fold this part. About this null PTR, we will discuss in my next episode. With this, now scroll up. We will implement this part. Long, parallel, fib, long, n, long, sum, fib, task. We have to pass cut off. For example, 4. L value reference A new TBB task allocate root. This is static member. See static. In this case, this is allocate child is not static member. Allocate child is not static member. In the global, allocate root is a static member. Here we say pip task for n comes from here. Then we pass sum as a pointer. Please note that new operator returns pointer we are taking as reference, so we need to dereference. I will make a line break like this. We created root node. Then here TBB task spawn root and weight. We pass A. This is once again static member. Now we return sum into main void test task blocking. Copy, paste it here. Oro pib 10. We are calling this function 10. Print pib 10 pib 10. Enter. Now open up your pretty board. Please understand that we have to use older version of Intel TBB. dir cd 018 task blocking CL EHSC SCD C++17 blocking .cpp fe m.exe. Hit enter. CLSM. The result is 55. This is correct result. In my next episode, we will do extensive experiments over pivot task. Please don't miss my next episode.